Okay, here we go. Let me go to this full screen here. There we go. And then I need to disable something here. There we go. Meeting controls. That should do it. Wonderful. All right. Welcome, everyone. So we'll be able to upload this recording to YouTube in due time. And then we're going to bring up some I guess I'll even try to keep track of the YouTube channel as well. Maybe people have questions there. I will try to answer what they have. But anyways, I'm gonna see if I can move these meeting controls around so that way they're not in the way. Okay, that's much better. All right. So today we're going to be talking about quantum devices and the different kind of shapes that they come in. There are many shapes that you can choose from. Some of them are nature inspired. Others are, well, really basic shapes. And some of them serve various purposes. And the one we have here today is going to be based off of nanostructures, which are all custom made. So next week we'll be able to talk about some other design aspects as far as the going into the clean room and things like that. So that's what's going on. Again, welcome. My name is Onri Jay Benally here at the University of Minnesota. And I'm working in the Department of Electrical and Computer Engineering. And I've been working here for quite some time, since 2018. And my boss, my PI, is Professor Jinping Wang. So, as far as the table of contents, we're just going to briefly go overview some of the motivations for why we build these quantum devices and kind of like the industry perspective of manufacturing quantum devices. And then we'll move on to some diagrams, basic diagrams of the quantum devices. I have mostly images to show you, and then also some 3D models. Later we can talk about how we can use maybe some data-driven 3D models for building the devices. We can do stuff like that. Sort of automated parts. But for today, we'll talk about the design of the devices. And then we'll move on to the layered architecture of a quantum system. Where does the quantum chip lie, which we spoke about before. And then we'll talk about some of the integrated components, because you can actually have qubits on a device, on a substrate, but those qubits need to be connected together and wired up somehow. And how are we able to wire up the components together? We'll be able to answer those questions. And then we'll look at some examples of qubits to give you an idea of what those chips look like. Lots of pictures again. And then we'll talk a bit about the modularity. In this case, the ability to swap out components very easily without having to rebuild some kind of specialized or proprietary components to interface with it. And then we'll get on to the conclusion. So here on the right side, again, this is a picture of a chip. This is a chip that I built, and this is a type of quantum device. But this particular device, it uses the tunneling mechanism, or like real quantum tunneling. And sometimes it's funny when I say that we can do quantum tunneling at room temperature, and then people think that, oh, don't you need low temperature to do that? Yes, you can do it at low temperature, but in this particular device, we are not tunneling phonons, or we're not necessarily dealing with these vibrational lattices, but instead we are tunneling the spin, the electron spin. And so those are things we can control inside of this device. And we can use it for memory. Um, we can use it for even some new kinds of logic. That's what that's for. So this is what the chip looks like. This is actually for a testing mechanism, testing setup. That's what this is for. So as far as the quantum system size, it's pretty much like this two-way arrow, as you would call it. Some of them are more desktop-like. So I drew up this 3D drawing of this desktop computer. And a lot of times people think about how small can we make these computing devices? Can I fit a quantum computer in my pocket? Things like that. So there's this idea that people have. They say, how can I fit, or how can I get a quantum computer for myself? And they ask all these valid questions, because these are some of the things that we've done with classical computing technology. But there is some inspiration here, and we'll talk about some of those examples. But the quantum computers that we have, they can become more server-like. When I say server-like, I'm talking about the size. It can fill up the entire room, all of the control components. Regardless, the size of the chip remains more or less the same in a small. You can hold it in your hand, the quantum chip, and even the CMOS chip that's used to control it. So, for that reason, people have been making these efforts, both in academic and the academic institutions, and also in industry, to try to make a CMOS chip, complementary metal oxide semiconductor chip, to control or miniaturize the control components that are as big as servers, and then put them into a small desktop machine. So that's a lot of work, actually, but you get the idea here. And here's like another 3D diagram showing how we get basic shapes of quantum devices. So there are various ones, and you can do like top-down manufacturing or bottom-up manufacturing, which you grow something or you slice it apart using some kind of energy beam, like ion beam, or maybe some other means like chemical etching that people try to experiment with. But those are isotropic. It's not exactly, you can't really get sharp defined features like this with chemical etching. You kind of have to use maybe like a reactive ion etching system or an ion beam etching. We'll talk about those in a future lecture. But regardless, we can get shapes like this using various nanotechnology fabrication methods, both in the academic setting and also in the industrial setting. So basically, you take a bulk structure. So let's just imagine this is a piece of metal. So there's just one giant chunk of metal. You can think of it as maybe 10 millimeter by 10 millimeter piece of metal by 10 millimeters. So 10 by 10 by 10. And then we want to take this structure and then grow a thin film onto a substrate. And then the thin film, we zoom in even further. The thin film you can grow these really thin layers of metals inside of here. And then you can get what is called a quantum well. So a quantum well is just this really thin structure that is stacked within these multi-layered films. So if you have some kind of film and it's like maybe 1 micron here or a couple of microns thick here, a couple of microns thick, then at least one of those structures, if you're using it for its quantum properties, then it needs to be on the scale of less than 100 nanometers. So we spoke about that in the previous lecture. And then when you want to make it into a nanowire, which is also called a quantum wire, or They're also known as 1D structure, one-dimensional structures. You can take something like this and then fabricate it in the laboratory, and then you could expose a beam of energy, put photoresist on here, do lithography, basically. And then you can create a nanowire, which does have some interesting ways of building up. But the point is, you take a thin film, you slice it, you expose it to a beam, and then you can make a nanowire. And then we can use this and then attach probes to either side of this wire to exploit whatever kind of properties that this metal or semi-metal or some other material is made of. And then if we want to make it into a quantum dot, then simply it's more or less the same process as these other materials here. It's just that you expose it to a smaller area and then cut everything else out. And then you're left with this tiny dot. So there are some other methods which involve using chemical solutions to try to condense sort of like nanoparticles or nanocrystals and then sort of place them onto the surface of a substrate. And then you would call it a quantum dot. And they can use it for various purposes. So the quantum device layer, of course, exists here at the bottom, the physical quantum processor. And this has all these components here. It says here that there are superconducting components, but that only applies to superconducting qubits in this example. However, for virtually every other kind of quantum chip that you are making, that exists here at the bottom here on this layer. So that's pretty straightforward. All of the control components, these can also be made of CMOS or what have you. It will exist here in this layer within the physical layer. Then there is of course, the software layer that exists, but that is beyond the scope of our lecture series, the software part. Maybe we can talk about the software that's used for building the chip itself, but not necessarily the software that's used to program the chip. So that's a little different. On the other hand, the name for this is just a quantum processing unit or QPU. So there's different kind of layers. And what does it say? Please do. Yeah. Yeah. So, and the other thing to note is a lot of quantum hardware is actually analog. There are a lot of analog components to pay attention to. So when you want to communicate with that quantum processing unit, you need an analog control down here, where all the digital controls lay up here. I wanted to show a diagram of some interesting diagram. I can share you some references. However, they are copyrighted, so I can't really show you those pictures. But if you want the references, I can show you some interesting references that show how the analog signal, where all of the analog signals are being used within this entire architecture compared to the digital signals. So those are also available. I'll make those available. And then when we move on to the digital control versus, or like if we can make a comparison between digital integrated chips, the 3D chips versus the quantum integrated chip, there's some interesting parallelisms between the two. Obviously, you have a substrate here at the bottom, and then there's this foundation for the chip itself. But then at the bottom, this is where the qubit arrays exist. Whereas for like an integrated semiconductor device, on this other hand, classical device, the digital logic, the transistors, all those components, the critical components are they're very small components. They're way down here at the bottom, and then that is controlled by some other analog component or some other signal that will allow you to control the logic or the flow of information between each and every one of these transistors that are on here on the bottom of this stack. And then these are just like the gold contacts or gold pads on top of the chip. And that goes, the same goes for a quantum integrated chip. There is there are these bit lines, these word lines, and then the transistor lies below that. But basically, on top of this, you would also have some gold contacts and gold pads that will connect to some interface that goes to a desktop PC, or it goes to some other automated system that's used for controlling these components, which controls these components on the bottom, which is the qubit array. So that's what this is. And then you can see here, there's an example. This is basically a 3D architecture of some quantum dots in a chip. So at the bottom here, there's a sort of cartoon representation showing that you have a bunch of spin orientations in these quantum dots, basically like nanocrystals that are deposited down here. And then it's connected to all of these sort of vias or metal contacts. And then these metal contacts can also be fabricated layer by layer, which will go up to the classical control components. So you could, in principle, place some CMOS components, CMOS control hardware on top of this, so that you could very easily miniaturize the entire quantum stack. Classical dash quantum stack, as people would call it. So there's a reference for that here. It's pretty recent, 2023. And then here, of course, just another reminder, here is an example of the system flow for the quantum control components versus where the chips would lie. So the chips, of course, they exist here way at the bottom of the stack. So this is what would be considered the bottom, and then all of the cryogenic systems, the cryogenic electronics that are resting here inside of this vacuum chamber that is held inside of the IBM Quantum System 1. Then that goes to all of these wires and coaxial cables, things like that. And then eventually to this analog control system here, which will interface to a digital to analog converter, which goes to a desktop PC. So you can see here another picture of a laptop. You can even use a laptop to interface together with this analog system, and then all that is just a way of automating the control for all these chips that are here at the bottom. So we will have some more talks and discussions on how those control components are carried out, and I'll show you some a bunch of pictures of some other systems that involve things like field programmable gate arrays, FPGAs, versus some other specialty made CMOS components, or even off the shelf components. You can kind of replace these systems here in that case. But this is one example of how everything has been progressing over the years. This is, of course, some other control components, the analog components that are connected to a PC. So here you have this PC, and then there's a bunch of wiring in the back, and whatever that's doing to automate this control system, it will give you the results more or less immediately. And then when you want to take the qubit readouts, when you want to take create an entanglement of the qubits together, then you can do that by controlling all these or modulating all of these components here in this analog control system. So again, in the back, you can see all these analog components, and then all those analog components, they're connected to some digital controls or digital to analog converters that will go to a PC. And again, you see here this cryogenic electronic system, and then you can replace the chip here. And then on the other hand, as I mentioned, you can miniaturize the entire system, and you can have a quantum desktop PC. It's like a quantum personal computer. So this is one such example. This is a real product that you can buy from a company called SpinQ or Gemini. Yeah, SpinQ. So this product is called Gemini 2, and you can buy this for about $5,000. It's a pretty small PC, desktop PC, relatively comparable with any sizable desktop PC. So you can sit this on your desk, and you can do quantum computation. You can read out the excited and the ground states, and then you can program it, and all the controls are done through this FPGA chip. So this FPGA here is connected to all these amplifiers, converters, and 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 such, which will connect to a PC. So here's a actually icon, a drawing of a PC that has this so-called spin quasar, or this is the name of the software that's being used to automate or control these nuclear magnetic resonance qubits in this desktop machine. So this is, I would say, this is a pretty neat example. Although it's used for only, or should I say, primarily for educational purposes, but it's still a pretty good tool that you could take as an example. And it's perhaps as the years go by, as time goes on, we'll be able to see more and more examples of how we're able to scale up the qubit architectures, the quantum architectures, together with off-the-shelf CMOS components, or with something that's more customizable, like this FPGA board here, that basically miniaturize the control components. So, of course, you probably recognize these. These are just qubits that are coupled together with a bunch of resonators. And I made these labels here to help you identify the components here. So basically, there are two qubits, transmon qubits, that are superconducting, and there's a readout resonator here, and there's a bus resonator here to couple these two together. So, interestingly enough, there are some other research efforts to miniaturize or decrease the footprint or decrease the area of these resonators here. So the resonator here, the only reason why they have these sort of meandering directions or meandering shapes is simply because it is to decrease the area or decrease the distance between these qubits. So you could place these two qubits very far apart, doesn't matter. But the resonator itself, it needs to connect to both of these two. But you don't always have the length of the resonator is not always modifiable. It has to be a certain length. So in order to compromise that, you have to squeeze it together, and you end up making these meandering shapes. So just like you would when you're like folding clothes. If you want to fold clothes, put it in a backpack or go traveling, then that makes it easier to transport it. but it's difficult to just have your clothes all laid out and then to try to travel with it. So this is the same case here. You're left with a specific length of wire, but in order to fit it onto a chip, then you can squeeze them together like this. But there are some other, like I said, research efforts where you can turn it into a sort of fractal architecture or fractal design to increase or decrease the area of which this line takes up. So all of this can fit into a small space technically, that is roughly the size of the transmon qubit itself, the qubit element. And then again, here is an example of where this chip lies. So as we are going to talk about in the future, there's some modularity here. You can fabricate a chip, and whenever you fabricate that chip, you can place it here in this little square, and then this square, as long as it has the right pin outs and the right plugins. Not when I say plugins, I mean the hardware interface, the little pins on there. If they if you can wire bond a new chip, a test chip, a design chip onto there, then it'd be much easier to run a bunch of tests on one chip after another chip after another. So this system is designed in such a way to make replacing those chips relatively easy. And again, here's an example of some trapped ion system qubits. So you can see some pictures of this the trapped ion system. So this one actually has tiny sort of magnets on there to help you couple or control the placement of these ions here. And then the ions themselves, they can be controlled by lasers, basically. So you have all these laser components that are opposite, that are what do you call it? Optically aligned with the qubits themselves, or you can try to add some other magnetic components to levitate or sort of put these ionic materials or atoms themselves, large atoms, and then try to manipulate the state of those atoms, these natural atoms in this case, as people call them. And then everything is written out here. I wrote it. There is I would say, yeah, right here. The most commonly used one is the ytterbium atoms. They're pretty large, relatively speaking. And again, here is an example of sort of the layout of the optical components needed for building some pretty early trapped ion computing systems. You can make, in this case, a replacement for this kind of control system by using nanophotonic chips. So instead of having an optical table like this where everything's laid out on a big table, you can try to miniaturize everything here using nanotechnology. You can take all these little grooves, I believe. Yes, that's here in this next slide. So there are all these little grooves that are etched using the same process for building CMOS components. And we'll talk about those next week. But basically, you can fabricate this silicon wafer here and etch all of these either glass components or silica-based components. And you basically have all these little grooves in here, these waveguides, and the waveguides will allow you to control or force these photons to interact with each other to create logic gates. Quantum, you can either choose to use it as a digital photonic logic gate, optical logic gate, or you can modify the configuration of this optical system to create a quantum logic of these photons interacting with each other. And all of that depends entirely on the way the waveguides are designed and the way the waveguides are fabricated. So you can see here, this is the same kind of setup you could replace. So this is just the logic gate itself, but you can replace all the other optical components or try to do so using a series of other smaller chips that will again miniaturize the photonic control. So there's a lot of effort into just making everything into chips. And if you can do that, then you can end up with a much smaller system that you can control or do computation with on a smaller machine. You can carry it around. You can say, oh, I got my quantum machine, and the fidelity or the quality of the qubits might be, okay quality. It might not necessarily have the highest fidelity in a much smaller system, but regardless, this is part of the progress. And then again, here is a wafer that's been fabricated at IBM Research, and this is one of the earlier devices. It's just multiple copies of chips here on the same wafer, and all of these are series of 5 qubits. So 5 qubits, 5 qubits, 5 qubits, all the way throughout. And then you just slice them apart, and then you can wire them up and place them on a testing bed, testing system, testing setup. So here are some examples of chips that I've made. You can see them here. These are, again, used for quantum tunneling. It could be at room temperature or at cryogenic temperatures, regardless. So this has the spin orbit torque components. Some of these are used primarily for creating a sort of like what is the term here? A stimulating coil. So this chip here on the middle right, you can see here there's an array of dots. It looks like dots to the eye, but under the microscope, these are actually tiny stimulating coils made of nanomagnets. And the whole point is you can connect these wires and wire bond them to each of these leads around the edge of this chip. And then what will happen is it will stimulate or create a manipulation of some kind of neuron. So you could take a neuron from a living creature and then deposit those neurons onto this. Well, you could place a microfluidic component on top of here, and then you can use this as a way to interact with those neurons. This is just an example of that. But regardless, all these components here, they are made with the nanofabrication methods in the laboratory. And some of these are used at cryogenic temperatures, others are used at room temperatures purely for testing methods, for testing purposes. So it's more or less complicated at various levels. And then there's an example here of the quantum device array being hooked up to or wire bonded to a PCB. So again, this is about the modularity. There are some pinouts here, and then you can exchange this out with another PCB that has wire bonded chips. And then what happens is you can plug these banana plugs or banana cables. Banana, what do you call them? Yeah, banana plugs. And then what you can do from here is try to test these components that are wire bonded here. So this is like multiple efforts between the testing team, the fabrication team. There's like a growth, like a thin film growth team, and then there's like a separate team that tries to work on sort of the theoretical development, theoretical calculation, numerical calculation, things like that. Regardless, it's a really big effort, and you can pretty much do the same thing with virtually every other kind of qubit. You can place them onto a chip and then just print out a circuit board, or you can fabricate a circuit board yourself. Then you can mount all of these interfaces that will allow you to interact with these qubits and then switch them out very easily. So it's very much like opening a desktop PC as well. It's if you want to upgrade the CPU in your desktop machine, maybe like your laptop, even not all laptops are serviceable like that, but many laptops, they have swappable CPUs. You can take out the CPU and then upgrade it with a new one, and it'll have better performance. And this is pretty much sort of following that same notion. And then again, here's the testing setup. Many kinds of testing setups for manipulating the quantum devices or testing them. They tend to have these probes, the testing probes. So this one on the left side is a testing probe from IBM Research. You take a chip and then you want to test the material properties of a single, maybe a single quantum device, or you want to test the material properties of some kind of new a new device where only one or two, maybe three leads need to be connected, then you can set up the stage like this. And then if you need a magnetic field to be exposed to it, then it's very easily set up. You can set up a magnet under here, or you can set up maybe a radio frequency microwave component under here, um, microwave control or microwave exposure of the chip. You can do that very easily. So this is the setup on the right. This is the setup on the that we have in my nanomagnetic testing laboratory. This is a facility we have where we can test the nanomagnets that are in these individual devices. And then here's an example of the IBM Quantum System 2, which is supposed to be coming online in the future. Basically, you have all of these. It's set up like a server, so it's a quantum server. So this is it's the exact reason why people from IBM are calling it the superconducting, or not superconducting, quantum-centric supercomputing. Because when you think of a supercomputer, it's pretty much a bunch of like modules, a bunch of servers in a giant server room. All of them are linked up together, very much like this. And then they have all of these GPUs and CPUs, memory banks, and data stores, things like that, all in this giant room. And what IBM is doing is they want to sort of do something similar. And instead of having a bunch of classical servers here, you would have a bunch of networks interlinked together using, well, in this case, microwave to optical transducer and optical fibers to connect all of these actual quantum computers. So the individual quantum computer here is represented by this sort of columnar hexagonal or hexagonal columnar structure. There's 3D diagram. And then you can create, in this case, sort of like a quantum server or like a supercomputer, but it's got quantum technology in it. So, and the quantum technology in it is used in this case for doing large scale quantum computation. So that's pretty much the direction we're going. And there's a market also for the desktop machines, as I mentioned before, which are currently for educational purposes. And then here's like a snapshot of the IBM System 2, Quantum System 2, again, from like a top-down view. So today we spoke about the qubits that we can make into quantum anharmonic oscillators. And they come in various shapes. They have like wire shapes, very simple wires. But the wires, you can sort of reshape the wires into some kind of arbitrary stringy shape that meanders in different directions. Or we can shape them into tiny dots, nanocrystals. We can manipulate these little dots, and then we can engineer them to behave as substitutes or as synthetic atoms. although it does have many atoms in it, but we can try to make it behave as if it's one atom. So we can also try to create quantum wells inside of the devices so that the quantum wells can allow us to exploit certain efficiencies of those quantum materials, whether if it's made of some kind of semiconductor component, like a 3-5 semiconductor that's often used in lasers, or maybe we can use it for trying to build a quantum logic gate. And we basically showed some examples of like superconducting, trapped ion photonic systems, and some other kind of chips. And then we also talked about like some CMOS components that we briefly mentioned, actually, that can be used to miniaturize the control components that are often bulky. And that will in the future enable us to build much larger quantum networks, because we are inevitably moving towards this million qubit architecture. And in order to meet the needs of those, or to basically interface with those kind of large qubit architectures, we're going to need to create some or miniaturize the control components for those. So that's kind of something we mentioned a little bit. And then, of course, we can create hybrid models which use many different shapes of quantum devices, and some of them we can leverage the interaction between or conversion between like a spin qubit versus a photonic qubit, things like that. And then next week, of course, we will move on to the fourth lecture out of 5. So that we'll be talking about nanofabrication methods. So the nanofabrication methods, it's often glossed over. It's often people just think you intuitively understand, or you already understand what it is, but it's much easier to see it from a generic model, comparing it to like 3D printing, other manufacturing methods like that, and then some other tooling that's used to make the quantum devices. These are not always straightforward, and even learning the software for those controls, nanofabrication control components, it's a lot of work. But if you can take it down, if you can take it from the very basic comparison versus some common household items or household appliances and tools, then you get a better idea of how those machines operate. And then you can even like at that point, if you understand it enough, you could attempt to build your own lithography system at home for fun, maybe. That makes up for an interesting project. So yeah. Anyways, so that is all for today. And if you have any questions about quantum chips, or even the control components of chips, I will be very happy and glad to recommend sources. I have many sources. I save them all. It's not on paper anymore. It's all on the Google Cloud. There's a notebook that I have called Google Keep. Okay, someone has a question. Relate. Mm-hmm. Yes. Yes. So every Wednesday at 4:30, that's correct. Central Standard Time. We do have the sessions. So we have 2 more sessions that are coming up. There'll be next week and then the week after that, which goes into May. So we'll be finished with this lecture series by May. Yeah. And then someone says, recommend resources for further learning, books, papers. Yes, definitely. You can look at some of them here in the slides that I'm presenting. I will also make the slides available on a Google Drive link, and then you can take some of the references from there. And then another one I would like to recommend is a list of quantum books. Let's see. One of them is a free resource, actually. His name is Oliver Ezrati. Let's see here. Okay, I need to bring up the controls again. Oliver Ezrati. I'm not sure if I'm even saying his name right. Let's see here. Oliver. I'm trying to make sure I'm spelling his name right. Oh, it's Olivier. here's a good first start. This covers a lot of information. The understanding quantum technologies. So the book that he's compiled. So that's one of them, and then I will provide some more later in the Discord. The other resource I will provide in the coming weeks is actually a paper. It's an article that I'm writing, and I'm almost finished with it. But basically, that article is going to have a bunch of open source images, open source references that talk about how the quantum device is made from a fabrication standpoint. And this is for both. This goes for both quantum devices and the CMOS components that we talked about, which are used for controlling the qubits. Yeah. So I will share that from the QuantumGrad website, and then it will also be shared on the Discord as well, and I think maybe Slack, the QuantumGrad Slack. So it'll be announced everywhere once it's uploaded to the site. So if there are no other questions, then I will see you guys in 1 week. Wonderful. Mm-hmm. Well, you guys take care, and we will be back. we'll have plenty to talk about. All right. Take care.